and welcome back to Concrete 101. My name is Ben Kaiser, and I am the Technical Services and Support Specialist at ACM Chemistries. Today we're going to talk about an aspect of concrete dry cast production that does not always get the attention it deserves: curing. The word cure makes me think of doctors and diseases, but in concrete it has quite a different meaning. It's more like curing meats like ham and salami. For example, when curing a nice ham, we don't just put it outside and hope something good happens. We have to provide space, heat, and humidity control for our ham. Otherwise, it's not going to turn out too well. For dry cast concrete, the curing process starts immediately after the unit leaves the machine. Controlled curing involves maintaining the desired moisture and temperature conditions both at depth and near the surface of the unit for extended periods of time. And the reason why we do this is because controlled curing plays an important role in the strength development and durability of concrete. Properly cured concrete has an adequate amount of moisture for continued hydration and strength development, volume stability, resistance to freezing and thawing, and abrasion and scaling resistance. Let's now go to Diane and see what she has to say about curing time.
The length of adequate curing time is dependent on the following factors: mixture proportions, specified strength, size and shape of the unit, ambient weather conditions, and future exposure conditions. Let's drill down on dry cast concrete units like pavers, SRW, and block or CMU. The process of making dry cast concrete products involves raw materials like aggregates and cement that are mixed with water, formed in a mold, and then cured for a period of time. Curing, or more specifically controlled curing, is what happens after the units exit the machine and before they are placed out in the yard. As you can see in the video, right when the dry cast units exit the machine, they're able to maintain their own shape and they look solid, but in fact they're quite soft, crumbly, and easily damaged. You can see how easy it is to break off a section with your hand. Controlled curing ensures that those units harden and maximize their potential for strength gain and durability. On the other side, incorrect curing can cause problems, and sometimes big problems. Controlled curing uses time, heat, and humidity. These are the three primary factors for controlled curing. Most facilities use some sort of enclosed chamber or room to control these factors. Here are some examples that you might see at your facility.
To understand why the dry cast concrete business uses controlled curing, it's mostly about time, as in time is money. This business model is based on high volume and efficiency, that means throughput, moving lots of product out the door as many days a year as practical. For most producers, local weather patterns just aren't hot enough to reach production goals, so we have to provide heat to speed up curing. So we know throughput is good for production. However, we are working with cement, and cement-based materials need time to develop sufficient strength to be handled and packaged without excessive breakage and culls, usually several days of time at ambient temperatures below 85 degrees Fahrenheit. Our goal then is find a way to work within the cement constraints and shorten the amount of time for the units to reach shipping strength. And the way to do this is by applying heat and humidity in a controlled environment. How can we do this? We know that concrete is made by mixing water, cement, and aggregates. When water and cement are mixed, it produces a chemical reaction called hydration. The cement and water hydration products form a glue, CSH gel, that hardens and binds all the aggregates together. For all the chemistry buffs out there, under what conditions will the cement hydration reaction not occur? Hang on to that thought and we will come back to it. Okay, so I can see some of you thinking, since shorter time is better and heat speeds things up, why don't we just put the units into a hot oven and have them done in a few hours? Sounds good, right? But the answer is no, no, no. That's a triple hard no. And that's because of how the cement hydration reaction works. Cement hydration is an exothermic reaction, which means that it gives off heat. You probably know that units will feel warm to the touch a few hours after they are made, even if the environment around them is cold. Here's a graphic of heat evolution during the hydration reaction. You can see it as a process, and it has a short beginning of a few hours, a longer middle of a few days, and then a very long end which can take years. At the very beginning, we see that the hydration reaction needs a minimum temperature to kick it off into the initial spike, and then it needs a period of a few hours to lie and be dormant before the hydration reaction products start to grow and strengthen. The dormant period is the foundation of hydration and is critical for strength development. It can make or break the unit. That is why it has been very important to not crank up the heat as soon as the units go into the curing chamber. If the heat is applied too soon, the units will crack due to insufficient strength. What this means for production is that there are parts of the curing process that cannot be skipped or rushed. After the dormant period, heat acceleration and hardening occurs. This is where heat and humidity settings are introduced in the kiln. If we match the cement hydration curve to the phases of a curing cycle, you can see they match up pretty well. That's not by accident.
Pop quiz time! We've seen how, in many climates, controlled curing is helpful to kickstart and optimize the cement hydration reaction, and thereby impact strength development. What a lot of folks don't realize is that curing, controlled or not, can affect the appearance of the units. Let's look at this picture. Here, we have 3 sets of pavers all made with the same raw materials, including the cement and aggregates. So here's the pop quiz question. Why do they look different? Well, surprise, surprise, it comes down to curing. The first set on the left was cured in an open bay, where the door was left open. The second set, in the middle, was cured in a closed bay that had added heat and humidity. The last set on the far right was the same system as the set in the middle, but the exhaust vents stayed open throughout the whole cycle, allowing moist, warm air to escape. So there was not sufficient humidity in the bay for optimized curing to occur. It's very tempting to think that as long as the products are placed in the kiln, you have done your bit and everything will be fine. As always, the devil is in the details. Simple actions like closing a door can make a big difference.
Let us now review the controllable factors that will impact cement hydration. Now, you may be lucky and live in an area where conditions are always perfect for curing, and you don't have to do anything. If this is normal for your facility, 24/7, 365 days a year, then congratulations, you can stop watching. For the rest of us, let's first dive into temperature. Over the last 100 years or so, the industry has learned that there is a sweet spot for curing temperatures, which is 85 degrees to 110 degrees Fahrenheit. At this temperature, curing will occur within a workable and predictable time frame. If the units are cured at less than 85 degrees Fahrenheit, times start to extend. If temperatures fall less than 55 degrees Fahrenheit, then things really start to slow down, and units are likely to be too fragile to handle even after 7 days. You may ask, when will cement hydration not occur? This happens when units freeze before they are properly cured. The chemical reaction is compromised and the units will never harden. On the flip side, units that are exposed to over 125 degrees Fahrenheit will gain initial strength very quickly, but the hydration reaction will not be complete and the units will not reach their full potential strength. At high temperatures, colors are affected and often start to fade. The graphic shows the effects of temperature on the hydration reaction. The green line shows controlled curing, with a nice even rise to the desired strength. Now let's say that you've nailed the temperature setting and you're right where you want to be. Is it sustainable? 85 to 110 degrees is pretty hot, and without the proper moisture, those concrete units can dry out and cease hydration. That's where humidity comes into play. Ideal hydration is at 85 to 95% relative humidity. It is important to note that we do not want condensation. There should be no drips. You can expect that to occur at 100% humidity, or at least prolonged exposure at that amount. On the opposite lower end, hydration slows and the surface dries out under 60% relative humidity. Even though warm and humid is good for hydration, it is important to note the kiln should be vented before removing units to allow them to cool and dry sufficiently. This minimizes shock and efflorescence potential. The amount of time required is a function of the controlled temperature and the humidity. It makes sense that if temperatures are low, More time will be required for the units to become strong enough to be palletized, moved, and placed out in the yard. Heat is recommended to be applied anywhere from 16 to 24 hours. If curing is too short, then we don't get the full benefit. If it's too long, then we run into the law of diminishing returns.
Hi folks, I'm Chuck from ACM and I'm a gardener. When some of my plants need that little extra boost, I'll move them here into the greenhouse. To make the plants grow and thrive, I have to provide the right conditions. Plants, very much like concrete products, need moisture and special care to become strong and useful. Moisture and heat will allow the seed and the soil in the pot to turn into a healthy plant. The wrong conditions, and we'll see very sluggish, weak growth and very bad plants. What are some of these special conditions? Is the greenhouse too warm? Maybe I've set the temperature way too high. And if I have, well, plants become dry and become very weak and thirsty. The plant becomes too brittle. I have a cull. Is my greenhouse too cold? What can happen then? Well, lower temperatures will never allow any of my plants to grow and reach their potential. All I have is this small, little starved plant that's actually used the same amount of potting soil and time and energy to just produce this. What if the humidity is set too high? Well, you'll know it. You'll see moisture all throughout the greenhouse. We'll have it on the glass, we'll have it dripping from the roofs, landing on my plants. I'll have puddles on the floor. It's just a waste of resource, water, and it makes a real mess. Well, that's enough of talking about ugly plants. Let's look at when I get it right. When I provide the perfect settings of heat, humidity, and even some air circulation. Now that's a beautiful plant, and anyone would be pleased to have that in their home or garden. Well, we're at the end of this part. Remember, greenhouses or even your kiln, they need special attention. And I'm gonna let you go now. I got homecoming season in Texas starting, and those 50-pound mums don't grow themselves.
Yes, mums. Of course. Thank you, Chuck. What do effective curing chambers have in common? No matter the type of curing, to produce a consistent product, you need to create a controlled environment of temperature, humidity, and time throughout your kiln and bay to bay. For instance, having variable temperatures and preset times will create products of not only different strengths, but also of different color and appearance. To achieve consistency, you'll need two things: circulation and insulation. You want air to circulate in your kiln so that all the products front to back and top to bottom are exposed to roughly the same temperature and humidity settings. You then want to insulate your kilns so that the warm, moist, circulating air cannot easily escape. Well, that's it for today. We hope you've enjoyed our little video on curing, and hopefully this helps paint a clearer picture of the purpose and effectiveness of controlled curing. Curing is the last stage of the production process, and that may make it easier to skip, but trust us, that's the last thing you want to do. Feel free to visit us at acmchem.com and to learn more about concrete technology at the ACM Academy.